So it's now time to implement the so-called softmax layer. And the problem is the following. So we now have our neural network where we have the layer for the input. So the input layer, then it passes on the information to the activation layer, which is a ReLU in our case, and it generates an output for a so-called output layer. And what we want to achieve at the end is that our network can categorize, for example, different images or different data points. So for example, I have a set of images where you can see cats and dogs and birds and many other objects. And therefore you have as many output neurons as you have categories, and you want to assign probabilities to the different classes or categories. So for example, I want to say, okay, this image shows a dog, this image shows a cat. And somehow we have to find a way to convert the outputs from the last layer into actual probabilities. We can't just guess a function or so. You kind of have to derive a function based on some mathematical laws that the whole thing actually makes sense at the end. And I want to illustrate the problem with a die, for example, where we have 6 different categories, so 6 different states. And then we want to create, for example, a neural network that assigns the different categories to what it sees. So for example, in an ideal world, we would get the following. So we have 6 output neurons because we have 6 different categories. And for example, if our category or if our state is 5, then all neurons should say 0 except the one which is responsible for this particular state, which is 5. So only this particular neuron should actually blink and should say, okay, the probability that this is a 5 is 100%, and the probability that's a 6 or it's a 4 or it's a 3 is 0. So that's an ideal world. And of course, in practice, we will have something like that. So still, the largest probability should be for the correct class or category, but there will be non-zero probabilities for all the other ones. So in fact, if we actually do this and really train with actual photos, for example, if you have a golden retriever or so, and it will still identify this as, let's say, golden retriever, but there will also be a probability that's, for example, tennis ball because it's yellow and has a kind of approximate shape or so. So it will not always be 0, 0, and 1. It will be something like that. And even though in both cases it has guessed the right state and the right class, there's still a difference between the classifications you see here and the classifications you see here. So there's a different quality. So here it's perfect. Here it's not perfect, even though it's both the same class. And one way to measure this quality is entropy. So I want to explain more about entropy in the next chapter, but just keep in mind that entropy is a measure of the categorization quality. There's an equation for entropy. I will not explain how to derive it. However, I will certainly upload a tutorial about entropy where I will explain this in more detail. But for now, it's okay if we just take this equation and see that we have these probabilities P for the different states I, and then we have the ln, so the logarithm, natural logarithm in this case, with pi, and then somehow we can calculate this quantity entropy. Again, I will explain this a bit more detail in the next chapter, but now let's just take this equation, entropy. It is important to understand that entropy has nothing to do with order or disorder. I know that people keep saying that, and there are lots of tutorials out there, but it's from the physics point of view just nonsense. It has nothing to do with that. What entropy is, however, is a measure of the amount of information which is available for the particular system. And I will not give a proof of that later, but I will show you an example, and it hopefully makes clear what entropy actually is. Because it's important to understand what actually is, what entropy is for the next steps. In general, if you do statistics, and also if you want to work with neural networks and evaluate the training process, then entropy plays a key role. So it really is very central for many approaches in statistics. And it really just measures the amount of information, or as you will see later, actually the lack of amount of information. And so, and that's the key point actually also to come to the so-called softmax layer. So the problem is that we have to convert the output from the output layer into probabilities. And how do we do that? So let's denote the output as epsilon I, and after it passed the ReLU layer, it constitutes values that go from 0 to infinity. And if we want to turn this into probabilities, the output has to range from 0 to 1. So there can't be a probability that's greater than 1 and that's less than 0. It doesn't make sense. And the question is now, what is an equation for this? So how do I turn this output epsilon I of this particular neuron into a probability for this particular class or category? So we're looking actually not for the probabilities themselves, we actually look for a function that turns epsilon into the probabilities. And there's one thing that we know for sure. So at the end, if we sum up these probabilities, it has to be 1. So the probability that it's any of those categories or any of those classes, of course, must be 1. So all the probabilities sum up to 1. And we also know that if epsilon is positive and we multiply this with the probability, we have something like a mean epsilon, because it's just a definition of the mean, which is also a positive value here. And based on this constraint, we can apply a recipe that's called maximum entropy. So maximum entropy means what? So as I said, entropy actually gives is the amount of lack of knowledge. So if entropy is high, you don't know a lot about the system. If it's low, you know more about the system. Again, I will show you this later in a few slides. But if we don't know anything about our probability distribution, if we just go from the last output to the probability, and we have no idea what the equation actually is to turn epsilon into probabilities, that's actually maximum entropy. So we have no idea what this function is. We apply those constraints, and then we will end up with an equation. And this is pretty common, for example, in statistical physics, and you will end up with a distribution that's called Boltzmann distribution. That I will show you the result. So the probabilities are assigned based on the output epsilon with an exponential, so e to the power of epsilon, and there's another factor beta, which I will explain in a few seconds. But as I said, there's a recipe that's called maximum entropy, and then you end up with these equations, and then of course have to normalize P, and then you have an equation. If you put it all together, this will be the equation. That's a so-called Boltzmann distribution. So again, you have the exponential of your input. There's a constant beta. I will show you in a few seconds what it means. And then you normalize by the sum over all the different outputs. So therefore, it's been normalized. So as I said, this recipe is called maximum entropy. And it would go too far actually to explain it in this context here. But I'm certainly gonna upload a tutorial about maximum entropy at this point. But if you like, I really encourage you to check out maximum entropy distributions and also in the context of Lagrangian multipliers, because it's also really helpful if you want to continue with data analysis and if you want to work with statistics quite a lot. Because you might have asked yourself, for example, why the normal distribution is so common and many data sets can be explained by a normal distribution. And it turns out it is also a maximum entropy distribution, and there's a reason for that. So I would really encourage you to Google for maximum entropy distribution, and there's a nice table on Wikipedia, and it will give you lots of insights actually where all these probability density distributions like a Poissonian binomial normal distribution actually come from. Again, for now, it would be too much. So I would just want to mention that the softmax layer, so this equation, doesn't come from nothing. In particular, it's not been guessed. Even if you read it in Stack Overflow, sometimes people were just saying, yeah, kind of guessing this, but it's not true. You can really derive it in a straightforward manner. And it's kind of adopted from statistical physics. And that's why it's called Boltzmann distribution, because Boltzmann discovered this distribution. So anyways, that's the distribution that turns our output from the output layer into actual probabilities. This normalization factor is usually called partition function with a capital C. If you see this at some point, that's just a normalization factor. In statistical physics, has an additional meaning, but we just ignore this for now. But you might see the idea already that there are lots of connections to statistical physics. If you work with neural networks and if you work on algorithm development, they all use, or mostly use, actually the ideas and the models from statistical physics. All right, so what is this mysterious beta? It depends on the context, actually. So if it's about actual physical systems, it's 1 over the temperature. In principle, that's one way how to understand why there's an absolute temperature you measure in Kelvin. It plays some role if it's about reinforced learning. In our case, temperature doesn't make sense. We don't have a physical temperature. We don't have an absolute temperature, which kind of defines the unit system. So we can just arbitrarily set beta to 1. So it doesn't play a role for us. And this function is called softmax in the community, as a contrast to hardmax. For example, you could look for the argument of the maximum epsilon, which is still used at some point. But again, as I said, the common softmax distribution is actually a Boltzmann distribution you can derive with this approach that's called maximum entropy. All right. Again, the details are a bit more complicated, and I would really encourage you, if you have time, to Google for that, and I would like to upload a tutorial in the near future. All right, so now we have a recipe, a mathematical recipe, to assign the outputs to actual probabilities. And therefore, we want to introduce a new class, the activation softmax layer. And also here, we just need to implement the forward pass so that we can pass the information from the output layer into our softmax layer. And we just have to compile this equation here. So first of all, we have the inputs, and we calculate e to the power of the inputs. However, this could actually lead to overflow quite easily. I mean, if you just picture that. So therefore, we kind of renormalize these values. That looks a bit like cheating, but it's actually not, for several reasons. So first of all, as long as we maintain the structure of this equation is mathematically correct, renormalizing actually refers to an arbitrary unit system. And then anyways, we normalize this with the partition function. So it still maintains the same structure. It's just for preventing overflow. So we still will have the correct results. So it's still based on a straightforward mathematical foundation. And then we calculate the probabilities by just normalizing this. And we have to sum up over the different neurons for every observation. And that's the reason why we have to be careful in which way we sum. And that's what we are doing here. So we sum across the different columns. That's why it's axis 1, right? Axis 0 would be the different rows in Python. And it has to keep the right orientations. That's why we say keep dimensions true. If that looks a bit mysterious to you, I will show you this in a few minutes when we set up the code and take a look at the output. But again, it's just we have to sum for every observation over the different probabilities. So over the different columns, so that we have a probability for every data point. And then, of course, we want to generate these probabilities as an output. And now we are actually ready for adders to our neural network. So therefore, let me just move to the to my user interface. Of course, we want to first of all set up a new folder. So we just call it softmax. And we also want to make sure that we navigate to this new folder. And we also want to save what we have already in this new folder. So we want to save our test function where we just test everything in this folder under the same name, and also we want to save our module. And then we just want to add our softmax layer. So I want to add the separator again, and then we just say class activation softmax. And we need the forward part with self and inputs. And now we calculate these values. So that would be already sufficient, but it will probably lead to overflow. So we will, so we want to normalize this with the maximum. And then we calculate the probabilities. Also here, I want to keep this in order. And we just divide those values by the sum over all the different output neurons, but for every single observation. So we sum this up over the different columns for each row. So we say axis equals 1 because it has to go across the different rows, across the different columns, but for every row. So again, I sum over the different columns for every row, because every row corresponds to an observation and every column corresponds to a different class. So the sum over the different classes has to be 1 for all observations, for every data point. And again, I'm going to show that. So now we have the output. And the probabilities are the output. All right, so then we can save our network. And then we just can add it to our structure we have here. So it appears already here in our module as a new class. And of course, we have to call the network again. That's what we are going to do here. And then we also want to initialize our activation. And this is now activation number 2. And I also want to use the autocomplete. And I also would recommend to do this in your case as well, because then you can always check whether it's been recognized already by the autocomplete. So I do this in the console just to make sure that it works. So you have activation reload and you have activation softmax. So the autocomplete works. That's a good sign. So it's been recognized as a class. So you can just add this. So now we initialize the layers and the activations. And what we want to do now is that we just add this here for the output. So we just then say activation. And the output from the dense layer number 2 will be the input of the activation. So let me also just show this again. So we have activation 2 now, and activation 2 has a forward part, and this forward part needs the input. So you also see this, here's the input. So this forward part needs the input, and the input comes from the dense layer here. So we can just copy and paste And here we have the dense layer. And this generates the output. And if we just do that, for example, if I just go back to the console here, we just also create more space now. If we use the autocomplete, it's not there yet because we still have to run the forward method, and then it creates the output. So let's do that. So just run this here first because we know that works already. All right. And then it creates an output and we feed it into the activation. And now it should create an output. So now we should actually see that. So we can go back to our console, use the autocomplete, and now we have the output. We can take a look at the output. So let's generate the output. All right. And let's call it out. All right. And let's see what we get. So we just generate the output now. And here it is. So let me expand this a bit. So what was the input? So if we look at the input, we have 2 data points, 4 dimensions each. And if we look at the output layer, we have n underscore neuron 2 neurons. So these are 6 neurons. So this is 6. Yeah? For example, if we have a die, we have 6 different states. So therefore, the output from the activation function should have the shape 2 times 6, because every data point can have one of those 6 states. So let's take a look at this. So first of all, let's determine the shape. And it's 2 times 6. So that looks good, first of all. So let's actually take a look at out. So for every data point, we now have these probabilities for the different states. So we have 6 different states because we have 6 different output neurons. Yeah, for example, if we roll a die, we have 6 different states. And we have 2 observations. So one die, the other die. So then therefore, the sum over these numbers has to be 1. Remember, we want to normalize it across the different columns for each row, because the columns correspond to different states and the rows correspond to the different observations. So let's just do that. So let's say sum, and then we want to calculate the sum of our output. And let's say from the first observation throughout the different columns, so throughout the different states. And this has to be 1. In fact, it's 1, of course, within the numerical accuracy. And of course, that has to be true for the second observation as well. And it's also 1. And now I hope it makes sense why we have to do this, right? We have to sum over the different columns in order to normalize for the probability. So that's our softmax layer. And of course, that's still not actual probabilities because our neural network still doesn't know how to learn, and we still haven't implemented. But nevertheless, let me just summarize what we did. And if we just go back to our PowerPoint, so we introduced this activation function softmax, which actually is a Boltzmann distribution. And again, we can derive it based on the approach maximum entropy, which is worth to look at if you like. I would really encourage you to do that. So that's our mathematical foundation for creating just the softmax layer. What we have now here is our input again. We have the different neurons. We have 2 different layers. We had the activation function, the relo, and now we have the softmax. And now we can create our network. So again, we have the first layer for the input, so the input layer. Then we have the activation, and then we have the dense layer. And now we added another layer with the softmax activation, which is this layer here. So we have the output from the output layer that just generates numbers, but now we know how to turn them into probabilities. And we also were just checking for the probability, so they really sum up to 1 across the columns for every row. So now we are actually kind of ready to work with data because now we want to, so the next step is that we define a loss function, and then we are already ready for the backpropagation part. So it makes sense now to load a data set. And as in the book, I would like to work with the spiral data set. You have different classes or categories. That's what you can see here. These are these different spiral arms, or like a galaxy or so. And we take the spiral data set, and also the authors in the book I recommended took the spiral data set because that was particularly tricky for the standard classification algorithms. Think about k-means or something. They would really not work in this case. So most of those classification algorithms actually failed. And that's one of those cases where it kind of only works with a neural network. Well, there are other methods how to do this, because if you know the shape a bit, you can work with that. So it's not entirely true. But again, it's a case where it outperforms most of the other standard cluster classification algorithms. So we can do this by using just pip install, and it's called nnfs, and then we can just import this data set, and then we can call this data set. The thing is, we can also call different classes. So for example, it can be 3 different classes, and the number of samples determines the number of samples per class. And then we have x, which is the coordinates. So actually x and y, and then we have y, which is the vector of the class, that it gives the vector of the class, and we want to take a look at this. So we want to call this and take a look at the output, and we also want to create a plot. So let me just go back to our user interface. So let me also just make some space here. So how would it work? So if we haven't installed it, I'll just say pip install nnfs. And might take a few seconds. So in my case, it says it's already there. If it's not, if you haven't installed it yet, so again, it would take just a few seconds. But now we just want to load the data set. And so we say just from an nnfs dot, and there's this data set. We import spiral data. Here's the, sorry, not sign data, spiral data. All right, so let's just import a data set. Then we also want to call the data set. So we generate x and y as an output. So we just call it spiral data. We want to have 200 samples per class. And let's say we want to have 3 different classes. All right, so here's the data set. Let's take a look at the data first of all. So let's start with x. Let's take a look at the shape. So it has 600 times 2, because we have 200 samples per class, so at 600. And as you saw on the plot, it's 2 coordinates, so like x and y. But you saw already that our neural network would work with any number of dimensions. So in our case now, it's just x and y, and we can also take a look at the first entry. So these are just the coordinates, x and y. Or you can also take another one if you like, just that you have an idea. And what is in the vector y? So what is the shape? It has the length 600, and this vector contains the class. So we have 3 different classes. We just print this. There are 0s, 1s, and 2s. Just to make sure, you can also use unique. And it tells you how many or what are the different classes without repetitions. So it's 0, 1, and 2 because we have these 2 different classes. So our vector encodes the classes with 0, 1, and 2. There would be another possibility actually. So for example, you can one-hot encode this. So for example, we have 3 classes. We have 600 data points. Then it could be a 600 times 3 matrix. And for the corresponding class, there would be a 1 and a 0 elsewhere. So that's the one-hot encoding. You might have heard about this, but I will talk about this in more detail in the next chapter. But as I said, there are different ways how to encode these classes. In our case, we just have one vector. And then, of course, we can also try to plot the data. And I want to do this with matplotlib. So we also have to import another library. And always import this as PLT. And then we can just create a plot. So we maybe should also write plotting the data. So I really want to just create a very simple plot, just a scatter plot. So first of all, we want to know where the different classes are because I want to create a plot where the different classes correspond to the different colors I want to see in the plot. So we first have to check where these different classes. Again, I want to keep it simple. So I can just, for example, use arg_where, and I can say, okay, if I know there are different classes 0, 1, and 2, then I can just look for y equals 0. Even though in this case, I know I can also separate it according to the indices. It might be not ordered. So it might be the case. So it actually makes more sense to make it more generic and to say, okay, I look for the values where y equals 0. And I just look at the indices, and let's call this index 0 because that's where the class is 0. Then I do this for 1. And of course, we can do this for 2. And we have the different indices. So these are all just vectors indicating where the statement is true. And now we can just set up a plot. So we want to just create a scatter plot. Really, I want to keep it simple. So it's not going to be a fancy plot. So just want to have X and Y. And of course, we want to have different colors. So we want to have, for example, for the first category, the first class, we just want to have black. And we also want to do this for the correct indices, of course. So here's one, here's another one. And now we just copy and paste it. And you see, I work a lot with copy and paste for 2 reasons. First, I'm lazy. And second, if the command is correct, then it also reduces the probability to make mistakes. However, if you have a typo in the first place, then you also inherited the typo. So there's also a downside to that. So we want to make this blue, and we want to make this red. All right, so then we just create this plot, and then we have an idea about the data. Let me just take a look at the plot. So I got the error message. So let me just quickly fix the error message. So what is the problem? So the problem is actually, so it's complaining that doesn't have the same size. I just want to remind you on the shape. X has the shape 6 times 2, and Y has the shape 600 times nothing. So we can solve this in a quick and dirty way. We just, sorry, that's of course true. So sorry, that was the, because we want to plot X and Y with different, so we want to plot the different coordinates with the different colors. So sorry, I was, could be confusing, of course, because Y is our vector of classes and it's not the Y coordinate. Okay, so now we have plot. And here we go. Here's another thing. And now we are ready. It's also an interesting plot, but it's not what we want. Okay, so we have different indices, 0, 1, 2, 0, 1, 2. And now we have our spiral data set. All right, so that's the spiral data set. And now we want to work with this data set. And the idea is that we want to train the network to learn which data point belongs to which class. And you see they're also partly overlapping. So that will be hard for any, most of the standard algorithms. So we are not that far yet. We have to do a few more things. And before we continue, we have to talk about loss and entropy. And I want to show you what loss and entropy is.